Yeah. So there are many works devoted to the search for the perfect and imperfect palindromes, and we consider imperfect case. So everybody knows what a palindrome is. It's a sequence that you can read from forward to backward and from backward to forward, and it will be the same sequence. And imperfect palindrome is basically a palindrome with gaps or and mismatches in some positions. And on the other hand, the added distance, which is basically used to compare two strings with respect of gaps and mismatches, can be calculated using dynamic programming. It's a pretty old result, but this result doesn't imply palindromic structures, and we're trying to cover this gap. So our work is kind of applied work in the field of computational biology, and in computational biology, well, basically in biology, we have nucleotides, which is from the point of mathematician just symbols in string, and we have 4 nucleotides. It is A, C, G, and T, or if we're talking about RNA, it's U. Oh, A, C, G, and U. And they form 2 complementary pairs. So A is complementary to T, and vice versa, and C is complementary to G. And next, the function C will denote the reverse complement. So basically, C of xy is C of y concatenated with C of x. And for example, C of AACG is equal to CGTT. And in DNA or RNA, a perfect palindrome is an inverted sequence repeat. So the string that is a reverse complement of itself. So later on, we won't use the concatenation symbol because it will be very long, I guess. And so the perfect palindromes are of the type X concatenated to C of X, where X is some sort of sequence. And from that definition, you can see that sequence of odd length can't be a perfect palindrome. And there are many examples of nucleotide sequences with perfect and imperfect palindromes, which is covered in one of the latest work of our lab. So to define how close string to being a palindrome, we introduce imp function. So if we have length of x, the imp of x is the ratio between minimal added distance between x and optimal palindrome to this length of this, and it is divided to the length of the sequence. And for example, we can see the palindrome, the sequence ATA-TGT, and the perfect palindrome optimal to that sequence would be ATA-TAT, as you can see from the previous slide. And so the added distance would be 1, and the imp of x would be 1 divided by 6. So this ratio shows how imperfect the palindrome is, and the correctness of this definition is based on the next theorem. In this presentation, there won't be proof of this theorem because it's kind of long. So there is a quadratic time algorithm that computes imp of x and the optimal partition of the x as the concatenation of w and z that minimizes the added distance between x and the palindrome w c of w. And the second theorem that I would like to talk about is the theory that imp of x is equal to imp of c of x, which was kind of counterintuitive on the first side. But actually, if we denote x as concatenation of w and z, since the prefixes match, distance between no. Oh, yeah. Yeah. Distance between x and wc of w is equals the distance between z and c at w, because the prefixes match. And since the suffixes match, also distance between x and c of z concatenated with z is equal to the distance between w and c of z. And of course, since distance between a and b is symmetric, and also distance is preserved if we compute reverse complement to both sides, it is true that distance between z and c and w is equal to distance between c and w and z, which is equal to distance between w and c of z. Thus, distance between x and w concatenated with c of w is equal to distance between x and concatenation of z, complement of z concatenated with z. And for all z, it is true that distance between x and c of z concatenated with z is equal to distance of c of x and c of z concatenated with z, because c of z and z is basically equals to c of z and z. Okay, I guess it was a hard one. And it is true because c of z concatenated with z is a palindrome by itself. And so the equality, the distance between x and w of c of concatenated with c of w is equal to c of x, distance between c of x and c of z concatenated with z. Okay, it was a strange moment, I guess. And also we can see that for all even length sequences, imp of x is not greater than 1/2, and for all odd length sequences, it is true that imp of x is greater than 0, but smaller than this side. It's pretty easy to prove that because distance from odd length sequence to a perfect palindrome is at least 1, so imp of x would not be 0. And if we divide, if we try to compute the right part, it would also show that the right part of an equation is also true. So we also computed the empirical dependency between median of imp of x and length of x for random nucleotide sequences. Well, we need to compute it with random sequences because, as you can see, 4 in power 60 is a pretty large number of sequences, and we can't compare them all. And you can see the fun fact that the median is greater than 1/4. Yeah. And there is also some interesting fact that you can see that it's kind of a periodic. We have 4 points, then 4 points, then 3 points, then 4 points, 4 points, 3 points, and it continues. We actually don't know right now why it's happening. Yeah. And also, we've computed the dependency between standard deviation of imp of x and length of x for the same sequences. And why we did that? Because it gives us some threshold in which we think that sequence is palindrome, imperfect palindrome, or it is not a palindrome at all. So if it's close to 0.2, we consider it's a palindrome. And if it's close to median or even bigger than median, we consider that it's not a palindrome. Okay. And we tried to kind of upgrade our look on it because if we analyze sequences, you can see it right here. Yeah, it's very often that sequence have this structure. This is palindromic part, and this is not palindromic part, and we have some not palindromic parts on the ends of the sequence. This structure is called hairpin or stem loop in molecular biology. And most of the biological sequences that are palindromic kind of look like this. So we thought that this part and this part, since it don't complement each other, let's just trim that off. And we created three functions called trimmers. So we're trying to find some substrings of our sequences. And we found this funny idea that since the algorithm in theorem number 1 also shows us the length of W, which are the beginnings of perfect palindromes, we can see that if W is pretty far enough from the middle of the sequence, then it could be because of this noisy part. So if it happens, we cut for the difference between middle of the sequence and lowest or highest W length. And all the three functions, prefix trimmer, suffix trimmer, and double trimmer takes as an input sequence X, sorted list of optimal lengths, but we actually don't need to sort it because when we are creating it, it's already sorted. And also we get a cutoff condition, which is a sort of threshold that we use. And yeah, as you can see, that minimal optimal length and maximal optimal length are the first and last elements of this array. Yeah. And so we check if this condition holds, that if RD, which is the difference between maximum optimal length and the middle of the sequence, we need to floor it because we counted from 0, I'm sorry. And if it is greater than length of x multiplied by cutoff condition, we cut the first RD symbols and from prefix. And if we have the second, I'm sorry, I forgot the word. Yeah, so we also have LD, and it is the difference between middle of sequence and minimal optimal length. And if it's greater than some percentage of x, we also cut off the last LD symbols. And we also have the third function that's basically do both things simultaneously. Yeah, so we also have we've proven the theorem that for a perfect palindrome, and if we have non-zero cutoff condition, we won't perform any trimming. And it's easy to prove because for a perfect palindrome, the only optimal partition would be precisely at length of x divided by 2 and floored. So the LD and RD will both be equal to 0. And 0 is obviously lower than 2 positive numbers, so no cutoff would be performed. And there's actually a difference between in which order we perform trimmings, and the second theorem about trimmers is for any n with at least 3 symbols, with length I'm sorry, for any x with length of at least 3, there exists a non-zero cutoff condition which satisfies both prefix and suffix trimming conditions, such that if we trim the suffix of sequence and trim the prefix of this sequence, it won't be the same as we firstly trim the prefix and after that trim the suffix. And there's a simple example of it. Let's consider this sequence of length alpha, where alpha is length of sequence divided by 2 floored multiplied by 2, and we add the 1 to results. So it would be the minimal odd number greater than or equal to n. And for that sequence, there will be exactly 2 optimal partitions. First would be on CL of n divided by 2 minus 1, and the second would be at CL of n divided by 2 plus 1. And the first one would correspond to the palindrome where we delete the last symbol, and the second would correspond to perfect palindrome when we add one symbol, t to the last, and it's squared shows that this is the final of the proof, but it's not. So we choose a cutoff condition as 1/10 divided by alpha, and it will be obviously smaller than just 1 divided by alpha, and so it would satisfy both trimming conditions, and the results would be both perfect palindromes but different ones. And the second trimming would not be performed to the first nor to the second strings. So in conclusion, we are confident that obtained results will be applied to prediction of imperfect palindromes. We actually did it on some microRNA data as well as we're doing it right now on some DNA data. And it is crucial to predicting gene expression regulations and RNA structures. And we have implementations of algorithms in Python. They're available to anyone on our site. And since it's really low computational, it has really low computational complexity, you could perform analysis on very large data sets. So I guess that's all that I wanted to talk about. Well, yeah, it's literature if someone is interested.